Hey everyone, let's keep going. So let's see, where are we? We are about to define Hilbert spaces, aren't we? Cool. All right, that's a cool topic. All right, it'd be nice if I had something to write with. I don't know that I have any here. Okay, well, we have to use those. All right. All right, these are terrible markers, but we'll work with them. Okay, so we have, just to quickly review, we have defined what a vector is, right? So a vector x, say x1, x2, x3 in three-dimensional, say, three-dimensional Euclidean space, right? Then this has to be given by some basis set, right? And the basis could be E1, E2, E3. And then these bases define the basis of my space, right? That define then E3. So this E1, E2, E3, right? And we said that instead of writing x, x1, e1 plus x2, e2 plus x3, e3, we decide to use this convention here, right? And write vectors by just specifying their coefficients, right? And that's very useful. And then with that, we define a vector space. Anyone can remind me what a vector space is? Okay, a set is a set of vectors. So I'm going to usually write this, right? Indicating set of vectors x, as we did with the affine space when we define the affine vector space, right? That obey two rules. One is the scaling. And so scaling is defined and closed. And we have addition, which is also defined and closed, right? Now the same applies to matrices. For example, to images. Images are nothing else than matrices, right? And we said if I have an image A and an image B, A plus B is going to be defined as adding the ith column of A with the ith column of B, right? Right? And if I have alpha A, that's the same as multiplying alpha by each of the entries in my matrix, right? Or my image. And with that, we define norms. A norm is a functional mapping F that abides or that complies with four rules. One is called the non-negativity, right? So the norm of my vector x or my matrix A has to always be positive or 0. Second one is it can only be equal to 0 if I have the vector matrix of zeros. The third one is scaling. If I multiply my function by a scalar, that's the same as multiplying the norm by the same scalar, the absolute value of that scalar. And the last one is a triangle inequality. So formally, we'll define a norm as a function that maps from, say, m by n, right now, or m by n because I have a matrix of m by n dimensions, onto just a real number, right? Just one real number. And given two elements, A and B, defined in that space of m and n dimensions, then f of A has to be larger or equal than 0. F of A can only be 0 if and only if A is equal to all zeros. It's a matrix of zeros. F of alpha A has to be equal to the absolute value of alpha times f of A. And the triangle inequality, A plus B, is equal to FA plus FB. Okay? There is another set of functions. What's that? I'm sorry. Yes, you're right. My bad. Smaller or equal. Thank you. There's another set of functions that are called quasi norms. And quasi norms are actually very interesting. They are functional mappings of that form that obey these first three rules, and they obey this last one up to a scalar. So I need to multiply this by some scalar, say beta. So beta f of A, f of B. Actually, this should be C, right? All right. Am I doing that wrong? Oh, I see what I'm saying. OK, yeah, sorry. OK, up to a scalar. And those are quasi norms. So for example, you know the norms that we have defined for vectors before. So if I have a vector norm P, P, for example, could be equal to 2. That would be the true norm, or the Euclidean distance, right? Euclidean norm. We have defined the Euclidean norm as what in 2D? As S1, right? Right? And P could be equal to, say, 4. The 4 norm would be something like this, right? You see how this works? So it's another circle. Obviously, according to the 4 norm, that other thing that I've drawn is a perfect circle, right? Because a circle, the definition of a circle is that all the points on that surface, right, of that circle are the same distance from the origin. Well, yeah, that depends on the norm, right? P could be equal to 1, right? It should give me this. This is the 1 norm, and so on. If P is between 0 and 1, but not 0 or 1, then that's a quasi-norm. It's not a norm, but it's a quasi-norm. Okay? And now you're going in the opposite direction as before, right? So you're doing something like that. And so on. Very interesting. They actually have a lot of applications. All right, so we saw the Frobenius norm. This is something to really, really remember about matrices. Which is for a matrix A, it's equal to the sum over all I and all j, all the rows, all the columns, aij square, and then the square root, right? And that, of course, has the same form. That equation has a 2 norm of vectors. But we derived in our last lecture the 2 norm for matrices, and that's different. Remember? That's a whole different equation. All right. Any questions about this? Can you move on? Okay, wonderful. So, whoops. So let me define more formally the inner product or scalar product. As we have seen multiple times in this class already, the inner product or scalar product is useful to calculate angles between vectors, right? Remember that? An inner product is an operator that takes in 2 vectors and outputs a scalar, right? Very good. But the inner product must obey, like the norm is a function that must obey certain rules. The inner product is also a function that must obey the following rule, x transpose y. By x transpose y, you can also write it as this, right? I mean the inner product of x with y, or the scalar product of x and y. Okay? Has to be equal to, anyone knows this? What's that? It has to be equal to y transpose x. Okay. So you can also write this is equal to this. Same thing. Now, in general, what we're going to do, we're going to say that x, y inner product has to be equal to yx complex conjugate. Okay? So this star here is generally used to specify complex conjugate. Okay? Now, if you are working with complex numbers, this is the complex conjugate. If you're in the real domain, that's a transpose. Right? The complex conjugate is going to be given by, so if I want to compute the complex conjugate, this is going to be given by the sum over all I of xi complex conjugate yi, right? So let me just write it this way. And now I can write a few more rules for the inner product with this new notation. If I have alpha x y, right, the inner product of alpha times x, right, this is just alpha a scalar, not a vector, right, times x, and that inner product with y, this has to be equal to the complex conjugate of alpha times the inner product of x and y. Yep. And if I have, let's see if someone knows this, x plus y inner product with z, this is equal to, anyone? No? Think about it for a second. What's that? Say that again.
The x inner product with z and the y inner product with z.
Very good. Excellent. So x inner product with z plus y inner product with z. Whoops. Excellent. Very good. Now, what is the inner product of x with itself? Okay, 0. And what else? Or actually, I'm sorry. What do I say? This is so wrong. I don't even know what I said that. This is, right? This is x squared, which is always positive. Okay, so larger than 0. And this is actually equal to 0. I'm going ahead of myself, right? If and only if. What's that? Yes, if x is the 0 vector. Okay, very good. All right, so we have all that we need to give our definition of Hilbert space. Now, before I do that, I want to tell you the truth. I'm going to lie to you. All right? Just to simplify things. Because otherwise, we'll be here next semester just trying to understand what Hilbert space is. Now, this, people, professors don't usually tell you that they're lying to you, but I prefer to be honest, right? And I'm going to give you a very simplified definition of a Hilbert, or a slightly simplified version of a definition of a Hilbert space. So here we go. My definition of a Hilbert space is a Hilbert space is a vector space and now we know what a vector space is, right? Don't we? Yes. Okay. So Hilbert space is a vector space for which its norm, so not only do we know what a vector space is, we also know what a norm is, right? Okay? And we also know what an inner product is. So a Hilbert space is a vector space for which its norm is defined by an inner product. Now, that's not the complete definition of a Hilbert space because it has to be complete, meaning that every Cauchy series has to converge in the space. Right, don't write it down, right? I don't want to have to spend another couple weeks covering Hilbert spaces, but this is the important part that we want to know, okay? All right. So for example, let's see an example of a Hilbert space. I'm going to define the norm of my vector space as the inner product x transpose x square root. A vector space whose norm is defined by this equation, which is given by an inner product, x transpose x square root, is a Hilbert space. This particular Hilbert space has another name, which is called the Euclidean space, right? So yeah, the Euclidean space is a Hilbert space. Obviously, the Hilbert space can be different than the Euclidean space, right? Any norm that's given by an inner product will give me, well, not every, as I said, there are some caveats, but in general, norms that are given by an inner product are going to define a Hilbert space. Now, a Hilbert space, it's a type of Banach space, okay? So Banach space is larger than Hilbert, right? Which is larger, for example, than the Euclidean. So the Euclidean space is a particular case of a Hilbert space, and the Hilbert space is a type of a Banach space. Now Banach was a famous mathematician, right? It's considered one of the fathers of functional analysis, what you will know as calculus these days, right? In engineering. Hilbert obviously was another famous mathematician. And Banach spaces have norms that may not be given by an inner product. Okay? May or may not be given by inner products. All right? So for what we are concerned here in image processing, and if you take computer vision, and in fact, if you take machine learning, even in machine learning, 99.9% of the algorithms that you'll see out there are defined in Hilbert spaces. There are a few, they're not, right? But it's the exception, not the rule. The majority of algorithms are defined in Hilbert spaces. And the reason is because every time that I can define things with an inner product makes computation so much easier to us if we want to implement them in a computer, okay? Inner products are great for computers. And these days with GPUs, I mean, makes it perfect, right? Makes it extremely useful. Okay, so there is a particular case of Hilbert spaces. Again, this is a particular case of Hilbert space, which give what's called an orthogonal expansion. So let's see what that means. Okay, the basis vectors of a space, say the basis vectors of a space, let's say F, okay, may be orthogonal to one another. For example, in the Euclidean space of p dimensions, the basis vectors are going to be E1, E2, EP. And orthogonal means that EI transpose EJ, meaning the inner product of two basis vectors, right, EI and EJ, is going to be equal to 0. And that's because they are at 90 degrees. And that means that for every I different than j, because if I and j are the same, then they are non-zero. Okay? Now recall, importantly, that any vector in my Hilbert space, in my vector space, can be defined as a linear combination of these basis vectors, right? So I can write this as any vector x in my space here can be written as the sum over all I, right, of EI times my coefficients, right? So let's use C for coefficients, CI, EI. So it's very important to know that these are called coefficients. Okay. And what are these coefficients? Well, these coefficients are nothing else than my vector x, right? My vector x inner product with my basis vector divided by anyone? By the norm of that basis vector, right? Which in the Euclidean is given by the simple inner product, right? So A transpose EI transpose EI. Excellent. So this is for vectors. Now let's extend this to tensors. Now, that does not only apply to vectors, as I said multiple times already. Vectors are not as special, right? It's not like, oh my gosh, all of this just works for vectors. Of course not. That's absurd, right? That works for anything else. So let's start with matrices, okay? The same can be done for matrices, the same that we have done here, in which case we will talk about the tensor product, okay? Okay. So for example, A and B, as we had before, defined in the real domain of M and N values. You could, I guess, you could also have it in the complex domain. Nothing stops you from having a matrix in the complex domain. The same applies to any domain, right? Real domain, complex domain. So if I am to define the inner product in the complex domain for two complex matrices A and B, I would say for every ij pair, right? Every I, every row, every column, I have Aij complex conjugate Bij, right? Tensor product. So far, so good. Now that means, as we did here, right? Remember, this is a linear combination of the basis vectors. Right? Right? Here, I can do the same thing. Right? I the basis matrices. Right? So if my bases are given by now capital UIs, right? So instead of now having my vectors, here my vectors, EIs, were defined in the real domain or complex domain of P dimensions. Now here, my UIs are defined in the real domain of M by N, right? Given those basis matrices, then I can write any other matrix as a, say, F, as a linear combination of my UIs times what else in here? Coefficients, CIs, right? Same thing. Let's see an example of this. All right. So let's see an example. How about if my basis matrices are the following? This is my basis set, okay? The bases are U0. Let's say that M and N are both equal to 2. Okay? So U0 is 1, 1, 1, 1. How about U1 is equal to negative 1, negative 1, 1, 1. U2 is equal to 1, 1, negative 1, negative 1. And U3, these are capital U's, is equal to negative 1, 1, 1, negative 1. Right? Okay. And I have a matrix F, right, in M by N, with F equal to, let's see, 0.5, 1, 0, 0.5. Okay. That's my matrix. Yep. And now what do I want to do? I want to write that matrix F as a linear combination of the bases, right? So this is going to be given by two things. One is the inner product of my matrix with my basis, right? The inner product of UI F divided by the inner product of the bases, right? So UI with itself. So if I do this, then I can compute the coefficients, right? So I'm going to have, see, 1, 2, 3, 4 coefficients, right? Let's call them Z0, Z1, 2, and 3, for these 4 different bases, right? Now remember that that's what I did with vectors, right? I don't write vectors like this, do I? I write vectors with only their coefficients, right? Right? So here I'm going to do the exact same thing. I'm going to write this matrix only with its coefficients, right? And I can apply this equation with the known inner product now to obtain these coefficients. And this coefficient vector, now this is a vector now, right? This is a vector. It's no longer a matrix. This is a vector, vector of coefficients. Is going to be 2/4. Where's this 2/4 and not 1/2? All right. Hopefully this is right. 1/4, 1/4, and 0. OK? I would assume this is 1/2. I'm not sure. OK. Yeah. Verify that I did the right calculations at home. OK? Now, why is that important? Can anyone tell me why in image processing we care about this?
So you can use several basic images to construct new images.
Very good. Excellent. Gold star. Right? Did you hear that? I can use a specific set of basis images to describe any other image I might have. Is that cool? So, for example, if I know what my basis images are, I can compute the coefficients of any new image with respect to that basis set, obtain this small coefficient vector, right? I mean, these basis images could be like 1 million entries, 10 million pixels, right? I could be, I don't know, 1 million by 1 million, 10 million by 10 million, whatever resolution you want. Huge. But this is only as long as the number of basis images. Maybe only have 20 or 30 or 100, right? Now, if I have that information, and you guys also know what the basis set is of images, I only have to send you the coefficients, and you can reconstruct any image. That's how communications work, right? And can you imagine if Netflix or HBO or whichever other channel you're subscribed to online had to send you all the pixels of every frame of every movie that you watch? You'd be insane. You will need huge bandwidth, right? It's absurd. YouTube, right? Which, how many videos are uploaded and watched online every single minute? It's insane. This is ridiculous. It's never going to happen. Well, because that's not how it works, right? Because the app that you download, right, the application that you install in your phone, in your tablet, in your TV, in your computer, knows what the basis images are. And all the sender has to send you is the vector of coefficients. And your application transforms this in an image in an instant. This is super efficient, right? All right, now the question is, obviously, what's that basis set, right? And we have to get to that. We'll get there, all right? This is one of the things that we'll be covering in the next few lectures, right? What's this basis set? But we know that there is a way to describe any matrix, meaning any image, using a finite, a small generally, but certainly finite number of basis images. Okay? Now, obviously, the same is done with sound, right, with music, with anything else. But here, because we talk about image processing, we care about images. OK. Now, if we change this basis set here, right? Say that this is a possible basis set, right? But if we change that, then what's going to happen? Then the coefficients are also going to change, right? This basis set changes the viewpoint or the representation, if you will, right, of the coordinate system by which that information is represented. This coordinate transformation is what we call a tensor. To see this, let's go back to something that we covered maybe first week of class or second week of class. Let's go back to a simple rotation defined with Euler angles. Okay. Now let's see how this relates to what we just did. So a possible rotation, to find a possible rotation, maybe, let's see, how about if I do the cosine of theta, sine of theta, negative the sine, and the cosine, right? These are the Euler angles that we defined early on. Remember that when we did this? It's a third lecture or something like that. OK, so if I have a vector, call it x1, x2, right? We have a vector here, x1, x2, with 2 entries. Now this is going to give me another 2-dimensional vector. Let's call it x1 prime, x2 prime. Right? And what does this do? Remember that all this does, it's a transformation of the coordinate system by applying a rotation from coordinate system, say, A to coordinate system B, right? And that was very useful to us when we're representing different cameras, right? So we're going to use this now to more formally define what we've covered before, but with the actual math that this should be explained with, which is tensors. So this thing here is a 2D rotation. Right? We also derived the 3D rotation, remember, in class. In the Euclidean space, right, E2. With a tensor, we can now more generally define any transformation, any 2D, obviously, transformation, with the matrix, let's say, L, and entries L11, L12, L21, L22. OK? Now, if we use this more general notation, I can rewrite this equation right here, right? This equation that I have as, let's see, I can define this as xi prime, right? The ith entry of this vector x prime. Okay? So this vector is the vector x prime. This is the vector x, right? So the ith entry of this vector is equal to the sum over all j, sorry, not I, obviously, all j of, let's see, xi, right, multiply by these two entries, which correspond to L, I, j, right, over all j's, right? Good. Oh, my gosh, another typo. That has to be xj, no? Oh, wait. This is Lij, yeah, Lj, right? Yes? Obviously. Okay? So far, so good? Now, this matrix L, a matrix L, which we define, say, in the real domain of m by n dimensions, is said to be orthogonal if and only if L transpose L, that means the inner product, it's equal to delta, a matrix that has diagonal elements different than 0 and off diagonal elements equal to 0. Okay, so it's a diagonal matrix with entries d11, d or delta mn, and 0 everywhere else. You will see this written sometimes also as diagonal delta 11, delta mn. Okay, both notations are equivalent. So this transformation that we had here that defines a rotation can now be generalized to this transformation called a tensor. And with that, we can provide the definition, the formal definition of a tensor. A quantity is a tensor if each of its free parameters or actually, why don't I say, to be clearer, more than parameters, we can say the suffices, right? So here, the suffices that I specify, the I and j's, right? Transforms according to the equation that we've given there. X prime is equal to the sum over all j of Lij times xj. Okay. Let's see an example, a more complicated example than what we've seen. I could define a tensor, capital Tij, or a transformation of the tensor Tij, is given by that transformation as, let's say, Tij prime is now going to be equal to the sum over all k and m of tkm here. And now I need to transform L Jm, right? Jm and L I k. Okay? Now with this, we can say, or we say, that the tensor has a rank or order, and the rank or order of a tensor is the number of free suffixes that I have. So for example, A is scalar, right? Scalar, just a value, a number. A scalar is a tensor. Now, of rank, what's a rank? Let's think. How many suffixes does a scalar have? One? Really? A scalar? Scalar is 0, right? It doesn't have any suffixes. It's just a number. So it's a tensor of rank 0. What else? A vector is a tensor of rank. How many suffixes in a tensor? In a vector, excuse me? Just one, right? Xi, right? X, it's a vector that has x1, x2, and so on, xp. So I have my xi's, right? And how many suffixes? It only has one suffix, right? So rank 1. A matrix is a tensor of rank, anyone? It's not a tricky question. 2, right? To specify the row and the column of that matrix, right? 2 suffixes. Now, a tensor of rank 3 obeys a rule that, let's see, Tijk prime. Now, if it's rank 3, it has to have 3 suffixes, right? And let's see, I am going to have here PQR, let's say, okay? PQR. And now I need to sum over P, Q, and R, right, for every possible triplet. So far, so good. And now I need 3 transformations, right? 3 transformations. The first one will transform from R to K. So let's say from R to K, so KR. The second one is transforming from J to Q, so JQ. And the first one from I to P, right? Yep, that's it. And you can go to rank 4 tensors, right? which case you're going to have 4 suffixes, and 5, and 6, and 7, and so on, right? So everything that you know about the scalars and vectors and matrices applies to any tensor of any rank, okay? You also hear that a tensor is said to be symmetric if Tij is equal to Tji. Well, in that case, let's say a second order or rank 2 tensor is symmetric if and only if Tij is equal to Tji. And is antisymmetric if anyone wants to guess or anyone knows. Very good. Negative Tij. I'm sorry, negative Tji, right? Tji. And you may remember the skew symmetric matrix that we saw early on. May sound familiar. All right, now that we know what a rank 3 tensor is, we can go back. Do I have time for this? Maybe let me set the framework, and then we'll finish this in our next lecture. We can go back to epipolar geometry, okay? Because the problem when we introduced epipolar geometry was that we didn't have enough math to actually go beyond what we covered, right? Now that we know all this, now we can go further than what we had. Now remember that in epipolar geometry we had 2 views, right? Meaning 2 cameras. And then with triangulation, right, we could compute the epipolar lines, the epipoles, the plane, and so on, the essential matrix, fundamental matrix. But we couldn't go beyond 2 cameras because we didn't know how to. We didn't have the math that is required to go beyond just 2 cameras. But now that we have tensors, we can actually do that. So I'm going to derive the result with 3 cameras, okay? All right. And those are called the trifocal tensors. So let's see, with 2 cameras, we had this model, right? Had 1 camera here, another camera there. We had a 3-dimensional capital P here that gets projected through the pinhole. This is a normalized image in front of the pinhole, right? So it's right side up instead of upside down. And this is with the second one. So here we had our epipoles, right? Here we had our small p prime, and that defines the epipolar lines L and L prime, right? You're all familiar with this by now, hopefully. Now, and especially for the final, right? You will remember that. And what happens if we have 3 cameras? Okay, let's see how we're going to do that. So this is going to be my first camera here. I'm going to have, say, a second camera right here. And now I'm going to have a third camera maybe here. How about that? Okay. Now, what I'm going to do is, instead of using a capital P point, I'm going to do derivations, which I could do with a P, but I'm going to do derivations with a line instead. Because now that I have 3 points, it turns out that I can work with lines instead of points. So I'd rather do this. So let's say that I have a line in my world, right? This line right here, okay? And now I'm going to take 3 pictures of that line using these 3 different pinhole cameras. So if I take a picture here, right, through the first pinhole, I'm going to get maybe this image. Here, I'm going to get this image here. And here, I'm going to get this image, okay? And I'm going to call this O, O prime, O prime prime. And this might be my line. And this is going to be my image of the line, my second image of the line, L prime, and my third image of the line, L prime prime. Now, each of these projections is given by a projection matrix, right? So I'm going to define this first projection here as a matrix, a 3x3 matrix, right? And a translation. I'm going to assume the identity matrix and no translation for the first one, right? I can do that because I said this is my starting point. And now this is going to be defined by this P prime is going to be defined by, say, a matrix A and a translation vector A. And this one, P prime prime, is going to be given by, say, B and a translation vector B, right? And now, obviously, this is given with respect to this, right? Which is the identity matrix. Now look at this. These 3 different projections, as I had here, right? This define a plane, right? See that plane pi? This projection of a line here also defines a plane prime, pi, right? And this one, pi prime and pi prime prime, right? So the same is true here. And how do I define these different planes? Remember, going to homogeneous coordinates, we derived the equation of a plane early on, which is nothing else than a matrix and a vector, right? The matrix, obviously, is our projection matrix, and the vector is obviously given by the coordinates of our line, right? So this is going to be PL. And what else? Pi prime is going to be equal to, what should be P transpose, excuse me. Pi prime should be equal to P prime transpose L prime and pi prime prime is capital P prime prime transpose L prime prime, right? Yes? Any questions? So far, so good? Okay. Now, for the first one, let's apply our transformation. What's our transformation here? It's the identity matrix in zeros, right? The column of zeros. So that means that this is going to be equal to L0, right? Am I right? How about this one? This one is going to be equal to, let's see, A times L prime and a small a times 1, right? Not 1, L prime, excuse me. A transpose L prime, yes. And the last one, same thing, B transpose L prime prime, B transpose L prime prime, yes? Okay, everyone okay? All right. So now we can define my tensor M, which is going to be equal to the entries of pi. We define that first plane here, the elements of the second plane, and the elements of the third plane. So let me write this using these different values that I have derived here. So M is equal to, let's see, the first one is pi. Pi is equal to this one right here, L0, right? So far, so good? Now, the second column is going to be given by this, right? So A transpose L prime, A transpose L prime. And the final column is going to be given by this term. So B transpose L prime prime, B transpose L prime prime, right? And I can rename this M1, as I've done many times, right? M3, the 3 columns of my matrix M. And I do this now because I want to write every column as a linear combination of the other ones, because there's a linear dependency. So I can write, for example, that M1, for example, M1 can be written as M2 plus M3 times some scalar, say alpha and beta. All right? Okay. Now, if I do this, now M1 is this, M2 is this, M3 is this. So I can solve for alpha and beta, right? And if I solve for alpha, it's going to be equal to B transpose L prime prime times some scalar. And beta is going to be equal to A transpose L prime times negative the scalar, okay? And K is some scalar. So what that means is that the ith coordinate of the line L, right, of my line, the ith coordinate of the line can be written as, right, this ith coordinate of this line, L, can be written as a linear combination of the elements of this and the elements of that, right? Sounds familiar, right? Going back to epipolar geometry, sounds familiar, right? Or should. So let's do that, and that's what's going to give us our trifocal tensor. Okay. So Li, now L sub I is the ith entry of the vector L that defines this line, right? So this is equal to a linear combination that is given by this equation that I have right here, right? This equation that is given by these coefficients, right? So I'm just going to write down these coefficients. I have BAI transpose times L prime prime transpose and L prime minus L prime transpose A BI transpose L prime prime. And I did this by simply substituting, right, these elements that I have on the other side of the whiteboard. Okay? Make sure that you check this derivation so you know how to do that. And now let me rearrange the terms here. I can also write this as L prime transpose times AI B transpose L prime prime minus L prime transpose A BI transpose L prime prime, right? So I only transpose this thing here. And that can be written as, now that I have, you see L prime transpose and L prime prime are the same here and here, right? You see that? So now I can do L prime transpose L prime prime, right? And now I have these two terms here, which I'm going to put them together in a tensor, right? Ti, where Ti is equal to AI B transpose minus A BI transpose. Now, how many of these tensors do I have? 3, right? For the 3 entries. So this is going to give me T1, T2, and T3. And this set is called the trifocal tensors. And these trifocal tensors define the transformation between one camera and the other cameras, right? You see that? In the same way that the essential matrix gives us a transformation from one camera to the other. The trifocal tensors give us a transformation for every possible camera to any other camera, and now for lines too. Now, obviously, tensors constitute Hilbert spaces for which addition, scaling, and the inner product are defined as we have given here in class today. Okay? Which means that everything that we did with the essential and the fundamental matrix also applies to the trifocal tensors. Now, deriving the results for more than 3 cameras is complicated. Okay? So I gave you a reference of a book, Multiview Geometry, if you're interested in digging more into this. I do cover a little bit more of that in my computer vision class. If you're interested, especially when it's related to, or it's used in the projective space, projective projection, which is very useful for many problems in image processing and computer vision. All right, any questions? No? All right, I'll leave it here. I'll see you next time.